In this lecture, I'm going to introduce the stress and strain in continua in a vectorial formulation that is very useful for the finite element formulations. This is the outline. First, we define the strain vector from the kinematic equations. This is the derivative of the displacement with respect of the positions, which is the axial strain in 1D deformations. In 3D, we define the gradient of the displacements that contains the strain. And we are going to convert this gradient of displacement into a matrix equations. E, this epsilon, is a matrix, this is another matrix, and this is the displacement field. So the matrix we are going to obtain is this one. We are going to see where this matrix comes from. Then we are going to define the stress as a vector from the static equations. So this is the balance of forces in 1D when there is only gravity forces. In 3D, we obtain these equations when the gravity can be in any arbitrary orientations in the three-dimensional space. And we are going to see that these equations can be converted in an equation like this, where this is going to be the stress vector, this is the body forces vector coming from here, and this is going to be the transpose of this matrix. And then the stress-strain relations, that in 1D is a scalar relations between the stress and the strains by the Young modulus. We saw that in 3D is the two quantities are like matrix or second rank tensors, and the strain-strain relations is given by a 4-rank tensor. This 4-rank tensor, it is like a matrix in the 4-dimensional space. So it's mathematically very complex. But if we define the strain and the stress like vectors, this can be written in a simplest way. So this is a vector, and D is going to be a 2x2 matrix. So we are going to see what is D and what is these vectors. So let's start with the kinematic equations in 3D. So the definition of the strain. So kinematics come from the word kinema, that means motion. So this is the definition of mathematical description of the motion of the deformations. So this is an infinitesimal element in 2D that is undeformed. And if the material that we are analyzing deform, so this square is going to deform. But first, this square have dimensions, infinitesimal dimensions delta x and delta y. And this is the deformed shape. So in the deformed shapes, every corner is going to have a certain displacements, and the inside of the element or the infinitesimal element, you have to have a displacement field. So this is in 2D. In 2D, this U, the displacement field, is a vector with two components, Ux and Uy, and these components depend on X and Y, the position in the plane. So the axial strain in the X directions can be defined by these equations that correspond to the partial derivative of the X displacement with respect to X. What does it mean, these equations? So you have this undeformed element, and you assume that the element deformed in this way, just a stretch in the X directions. So in this case, so the strain is calculated by the deformations in these directions that is the deformation of this size minus deformation of this size, divided by the length of the element. And then in the limit, when delta x is very small, this dot means limit. When delta x and delta y is equal to 0, then we get the partial derivative of the x displacement with respect of x, which is the definition of the axial strain. So in the same way, the axial strain in the y directions is defined like this, and is related with axial deformations in the y directions. And then we can define the simple shear in the x directions by these expressions. This is cross derivatives, the derivative of the ux displacement with respect of y, and the interpretation of this deformation is given by these simple shear deformations. So this bottom and this top move relatively in the x directions to produce a shear motions, and the simple shear strain is going to be the difference between the x displacement divided by the height of the element. So this is the simple shear in the x directions, and you can define the simple shear in the y directions in the same way. It's going to be a shear in the y directions. So these are the components of the so-called gradient of displacements. And from this gradient of displacement, we can get the three components in the plane for the strain vector. So first, we define the pure shear strain in the xy plane by doing a linear combination of these two deformation modes. If I combine these two deformation modes, I get the pure shear strain that is represented by superposing this deformation with these deformations. So this is a pure shear deformations. It's pure because it doesn't evolve change of volume. But here we are assuming that the displacement is very small. So these displacements are much smaller than the size of the element. Okay. So also we can define the pure rotational strain in the xy plane. That is the linear combination of this one minus this one. So if I subtract this deformation from these deformations, so I get the rotational strain that corresponds to this kind of deformation. This kind of deformations is a pure rotations, and this deformation doesn't change the strain in the element because the element is not deformed, so the stress is not going to change. So this rotation is not part of the stress-strain relations. It's going to be put it out of the equations. So we are going to put the axial strains and the pure shear strain in the stress-strain relations. We can extend these derivations in 3D. So in 3D, we have all components of the strain are this one. You have an axial strain in the x directions, an axial strain in the y directions, an axial strain in the z directions, a pure shear stress in the xy plane, in the yz plane, and in zx plane. You have also three pure rotations that are not going to affect the stress, so they are not included in the relationship. So we can write this in a matrix form. So here I am writing again all the equations for the strain, and I will put all these components of the strain in a vector, a 6-dimensional column vector. And comparing with these equations here, I can write this as a relation between these components. These components are the x, y component of the displacement field. So I can connect this with a matrix with derivatives here. And if you compare these ones with this here, you can identify the matrix here. For example, in these terms, exx is the partial derivative of ux. And the gamma xy is going to be dxy minus the y dx, and so on. So this is a matrix representation of the kinematic equation. Can be written in a very simple way. So this is the strain vector, this is the displacement vector, and this is called the operator. It's operator because it operates in a vector to convert this into other vectors by making derivatives, the L operator. Now we are going to go to the derivation of the stress components of the stress vector. So this is the static analysis. So for the stress, I'm going to take a infinitesimal plane oriented in the x directions in a certain point in the three-dimensional space. This plane so this plane area, the area of this plane is going to be delta AX. Delta A because it's going to be infinitesimal area, and X because it's perpendicular to the X direction. And the stress is going to define the axial stress, sigma xx is going to define as the limit of this force over this area. That is going to be force xx. What is force xx? So this is, in this area, I'm going to have an axion reaction 4. That is in general, is going to be a vector in any directions. And then I project this vector in the x, y, and z plane. So this is perpendicular projections. Probably this doesn't look like perpendicular, but it's assumed that it's perpendicular. So this is the perpendicular projections. And so it means that this vector have three components. So this is the components xx, yx, and zx. So the first x means the plane where this force is acting, and the second is the component of the force in the Cartesian coordinates. So this is the definition of the first component of the stress, and you can also define these two components of the stress that are called shear stress components. In the same way, we can do the same definitions of stress in the other two planes. One plane perpendicular to the y directions, the blue one, another plane perpendicular to the z directions, that is the orange one. And then for each plane we can define three different forces and three different components of the stress. So this is the axial stress. Now the first one was the shear stress, and then you have an axial stress and another shear stress, and these are the components in the z direction. So in total you have 9 components of the stress tensor, and this stress tensor is called the Cauchy stress tensor. After definitions of the Cauchy stress tensor, we are going to derive the static equations. So to the derivations we need an infinitesimal cubic element. If we are going to derive the static equations in 2D, or we can do a xy cut of this cube to get the static equations in 2D. So here I have put all the forces acting in the element. In this 2D diagram, I also put the body forces. And here is all the component of the stress in 2D. So we need to do the balance of forces in this element. So what we do is equilibrium of forces. So we have to calculate all the forces in this element. So let's start from assuming that this point is xy. it means that this point is x plus delta x2 y, and this point is going to be x minus delta x2 y. Yes. So this force, the force here, the first force is going to be the stress in this point, is this one, multiplied by the area. So multiply by delta x, and I should multiply by delta z, but I'm doing this in assuming that this plane. Yes. So this is going to the force, and then I need to multiply by delta y and everything by delta z that I haven't included here for simplifications, but it's going to appear in all the equations, so I didn't include this here. So this component is the force here. Yes, and we are doing the sum of the forces in x only. So I'm going to have this force here that is calculated x y plus delta y2, and I have to multiply by the area, that is delta x delta z, that I didn't include here, but everything should be multiplied by delta z. And then I have the body force in the x direction, so it's going to be this quantity, that is force per unit of volume, like unit weight, and it's going to be multiplied by the volume, that is going to be equal to delta x, delta y, and delta z. So you can see that everything is multiplied by delta z, but I didn't include it because it's going to be too long and it's not going to fit my space here. But it's a common denominator that you can cancel at the end, delta z. Now we are going to divide by delta x, delta y, all these equations, and then I get this. Divide them by delta x, delta y, I get here a term, another term, and these terms can be approximated by a partial derivative of sigma xx with respect of x, and this is going to be the partial derivative of sigma yx with respect of y. And this is the unit weight. So then, taking delta x to 0 and delta y to 0, infinitesimal element, then you convert these equations into these equations. So this is the static equations in 2D in the x directions. So we can repeat the same derivations by summing all the force in the y directions, and we are going to get another equation similar to this one that I'm not going to include here. So I'm going to go to another equations, that is the equilibrium not of the forces but the equilibrium of moments. So equilibrium of moments will lead to the symmetry of the Cauchy stress tensor. So we are going to sum all the moments in the z directions for this free body diagram. So here I'm calculating the moments. Let's see. So the first component is xy in x plus delta x divided by 2, y is this component xy, sigma xy in this point, x plus delta x2, y, and a given zeta, and then this is the arm of this force. So it's going to be, no, the arm of this force is this one, delta x2, this is the arm, and then I have to multiply by the area to get the proper moment units. So here I have to multiply by delta y, and of course by delta z. I didn't include delta z because it's going to appear in all the components of these equations. So this times delta z is the moment due to this force. Now I can include the moment due to this component of force, that is going to be the same component of the stress but calculated in another point, x plus delta x divided by 2 yz. This is the arm of this force, of this moment, and this is going to be related with the area. Delta y, delta z is the area. Then I need to include the moment of this force, so this moment is going to be negative, and it's given by this component. This is the stress, the arm, and the area is going to be delta x, delta z. Delta x, delta z, and then the moment of this force is this one. And this is all because these moments are calculated with respect to these points, so the body forces are not producing any moment. And after I write the force components of the moment, I'm going to rearrange by dividing everything by delta x, delta y, delta x, delta y divided by 2. So I get these equations. So this is equal to 0. That is equal to 0. This is a bit redundant. Please ignore these two equals. So everything is equal to 0. And then I can take delta x and delta y infinitesimal. If you take delta x and delta y infinitesimal, you can remove this and this from these equations, and you're going to get 2 sigma xy, and here the same, 2 sigma yx, that is going to be 0. Which is equivalent to say that sigma xy is equal to sigma yx. In summary, the balance of moments will result in asymmetry in the Cauchy stress tensor. So sigma xy is equal to sigma yx. And this is going to valid for all the components. This means that the Cauchy stress tensor is symmetric. In summary, the balance of moments results in the symmetry of the Cauchy stress tensor. Let's write the equations in 3D. So in 3D you have these equations. So balance of forces in X, balance of forces in Y, balance of forces in Z. And then balance of moments, before of the balance of moments, so we can define a vector of 6 components. Only 6 components, not 9, because sigma xy is going to be equal to sigma yx, and so on. So we have 6 components. And these equations can be replaced by this operator applying to these equations. And then this part of the equations can be written like this. So this balance of linear momentum or balance of forces results into these equations. It's a matrix equations. So this is going to be the transpose of the L matrix. This is the stress vector. This is the body forces vector or unit weight vector, and this is zero vector. So remember that this was L, and you can identify that this one is the transpose of L. So this L appear in the kinematic equations and in the static equations, but in the static equations appear transpose. So these equations can be written in like this: transpose of L multiplied by the stress vector plus the body force vectors is equal to 0. The balance of angular momentum, or the balance of torques in equilibrium, is going to give you these 3 equations. So it means that you don't really need to put 9 components here, but only 6 components, because sigma xy is equal to sigma yx, sigma xz is equal to sigma zy, and so on. Now we go to the constitutive equation. So the constitutive equation is going to be defined by a matrix that relates the component of the strain with the component of the stress. It's going to be a 6 by 6 matrix. But I'm going to introduce a simplified version of this matrix using these assumptions. So I'm going to assume linear response. It means that if I apply different actions, the response of this action, that is the strain, is going to be the sum of the response of this individual action is equal to the response of the combination of these actions. This is linear response assumption. Or it's also called principle of superpositions. And I'm going to assume isotropic elasticity, which means that the material will be assumed to respond in the same way in all directions x, y, and z. Under these assumptions, so the constitutive relations is going to be this one. So this is the linear elasticity relations between the stress and the strain vector. This is the Young modulus, the Poisson ratio, and this is the shear modulus. That is not independent, but it depends on the other two quantities by this relation. So this is obtained using these two principles or two assumptions. But it doesn't mean that all materials satisfy these equations. If the material is nonlinear, materially nonlinear, these equations is going to be more complicated. And if the material is anisotropic, like timber or composites, so you're going to have many Young modulus and many Poisson ratio, 2 or 3, depending on the degree of anisotropy. Non-linear response usually indicates that the Young modulus or the Poisson ratio depend on the stress level. And this can be analyzed using material nonlinearity analysis in finite element analysis. Okay, in summary, so we introduce the constitutive relations of the linear elasticity and anisotropic linear elasticity. So the relationship is this one. Here we have 6 components of the strain, and we remove the 3 rotational strain components that doesn't affect the stress. Here we have the 6 component of the Cauchy stress tensor. We reduce the components from 9 to 6 using the symmetry of the stress tensor, resulting from the balance of torques, of moments, balance of moments. So we have that the shear modulus in these equations is depending on Young modulus and the Poisson ratio, and we can invert this matrix and we can express the stress vector in terms of the strain vector. This is the invert of this matrix. And here I have again the shear modulus and another quantity that is called the Lamé constant. That is given also in terms of the Young modulus and the Poisson ratio. And this is the summary of the linear isotropic elasticity.